Let's take a quick look at the abstract world of atomic structure. The protons are in the middle, the electrons go around the outside. The electrons are in energy levels. There's 2 electrons in the first energy level, 8 electrons in the second energy level, and 8 electrons in the third energy level. The octet rule tells us that the energy levels need to be full. By way of review, let's look at these 2 examples. We have hydrogen. This is right off the periodic table. Hydrogen has a proton and an electron, violating the octet rule. It's the duet rule in the case of hydrogen. And then oxygen has 6 electrons in the outer energy level, again violating the octet rule. A common structure, perhaps the most common structure in the universe, is this one, which is H2O, which is water. The oxygen has a covalent bond with 2 hydrogen atoms, giving the hydrogen the 2 electrons it needs, and the oxygen the 8 electrons that it needs. Water, both the oxygen and the hydrogens, meet the octet rule. The oxygen has 8, the hydrogens each have 2. A familiar reaction of water is that it dissociates into the hydrogen ion and the hydroxyl ion. If we look at the hydrogen ion, we see that it's a proton. It's a proton with no electron, and it has a positive charge. And you look at it and you might say, well, it's unstable because it has a positive charge, but that's not the case at all. It's stable because it has a negative charge. And then if we look at the hydroxyl ion, we see that it has 8 electrons, but it has to have an extra electron, giving it a negative charge. So similarly, you might look at the hydroxyl ion and say it's unstable because it has a negative charge, but it's the negative charge that makes it meet that octet rule, and it's the negative charge that makes it stable. This is, of course, the hydrogen is, of course, acid, and the hydroxyl is, of course, basic. And if either of these is in high concentration, they can be reactive, but just as an individual particle, they're not reactive at all. Let's assume that water will dissociate into a hydrogen atom and a hydroxyl free radical. Okay, now if we look at this hydrogen atom, we see that this is a hydrogen proton and an electron. It's electrically neutral. This particle may be the most reactive particle in all of chemistry. It violates the duet rule. The hydrogen needs 2 electrons and it only has 1. And the result of this is that the hydrogen free radical has a half-life of 1/1000th of a second. When it appears in cells, which it does sometimes, the hydrogen free radical, it doesn't go looking for something to react with. It reacts with the first thing it comes to. And the first thing it comes to may very well be an aliphatic hydrogen, like the tail of a fatty acid, like a lipid. The way this works is that the hydrogen free radical finds a hydrogen, pulls it off as another free radical, and then the 2 free radicals combine to form hydrogen gas. This is a typical theme in free radical chemistry, is that 2 free radicals will typically neutralize each other. And then the hydroxyl free radical, notice the Lewis structure, we now have 7, is missing an electron. The hydroxyl free radical is somewhat less reactive, quite a bit more common in cellular biology, and the reaction is the same. It doesn't react with something, it doesn't choose something to react with, it reacts with the first thing it comes to. The chemistry is complex, but again, it's a high likelihood that it will react with another hydrogen off of a aliphatic carbon compound, and it'll pull this guy right out of here, and as a free radical, the 2 free radicals, now in this case it's the hydrogen free radical and the hydroxyl free radical, will combine to form H2O. We'll go right back to water. And in both of these cases, it leaves behind a free radical. It leaves a scar on the material that it attacked. This is like the empty chair in the stadium. Part of my intuitive understanding of free radicals is that they're not very common. Two free radicals will frequently neutralize each other, but free radicals are not very common, and the likelihood of two of them coming together is not high. When I was a chemistry student, I was not a very smart kid. The teacher would say, oh, free radicals are unpaired electrons. And I'd go, oh, free radicals are unpaired electrons. Okay. It's easier for me to see it as free radicals are violations of the octet rule. And that's it.